Audio on, yep. Okay, so this is part D. So for a methanol isopropanol liquid feed of 1 mole, 45% mole methanol, so ZF equals methanol, or ZF equals 0.45. The desired methanol molar recovery of 0.98 and 99% mole purity in the distillate. So XD equals 0.99. Explain and write code to generate automated Ponchon-Savart diagrams for reflux ratios varying from close to minimum reflux ratio to what is practically infinite reflux ratio. Okay, so we have our given parameters right here. What did they say it is? Methanol isopropanol. For some reason, I had benzene toluene. Methanol isopropanol. Run cell in below. There we go. Okay, so this is all the code that we had for part A and B. So we get new TXY diagrams and a new XY diagram from this. No more azeotrope. So let's go ahead and get started. Our D is going to be, or I guess RD is 0.98. So that means, so we have recovery in the distillate of 0.98 of our more volatile components. So that means the recovery in the bottoms is simply 0.02, so 2%. And our distillate, we are getting from our moles coming into the feed, we have 0.98 of that, so RD divided by XD. Okay, so we have D. Then B would follow the same format, although it would be XB. And we haven't defined what B or XB is, so we'll actually have to do B first. And that's, we get that from a simple mole balance. So F minus D is equal to our B. And then we would switch the B and the XB here. So XB would be all of this. Now we need to get arrays for our liquid and vapor enthalpy. So that's going to be, it's going to be similar to what we did over here. We're going to have, oh, and I forgot. All that I have pulled up in this book is just that last bit that we were doing in... that doesn't make any bigger. That last bit that we were doing on part C. Just because there's a lot of math and a lot of energy balances that we have to work on in this part, and it makes it easier if I don't have to try to do the algebra in my head, and I can just refer back to what I had written down. So we're going to have HV. We need an array of our HLs as well. Going to have for X1 T X1 Y1 and yeah, it'd be in those. It would be appending the HV dot append dot HV what are we would want, if it's V, we want Y1 Y1. We need our value for T as well. Same thing for liquid, although these needs to be X1. All right. Then we're going to use the interpolator as well, although this needs to be now HV interpolate. And then HL. And then we have HV L, HL, and this is HL, HV. All right. Now we need, so let's get our QC values. So we're going to get this from the equation that we were working on when we set our energy balance equal to our reflux ratio. We can't do that for QB, but we can do an overall mass balance of just our entire system, which is actually a little bit more simple than doing an individual condenser or boiler. So we're going to do, let me write it on paper because that would be easier in my head. That's going to be, do we have our liquid? No, we just have it in terms of R. Okay. In terms of R&D. Okay, that'll work. We have R, H, V, and plus 1. Equals Q, C for D plus H, D. Plus H, V, and plus 1. Multiply everything by D and move it over. So then we have I guess we can find, I mean, L would just be R times D. So here's what we have for QC. So QC equals be R times D. And then we have our heat of vaporization. So we need P dot H vaporization. And that would be, I guess all of these would be at composition XD. Well, did that give us two values of QC though? Let's try this and then see what happens. So P dot HV and then P dot HL. Right. Then plus HV minus HL. Okay, so then we're going to need our delta R, and that's simply delta is equal to our QC divided by D plus HD. That might be kind of tricky. We'll come back to that. Okay, and then our QB. So let me do the mass balance on this side of the page. So that would be energy going in. So F times, I guess, times Z times HV or HL, and then oh shoot. Okay, let me write. This is going to take a minute. Let me just do it off screen. All right, so we slipped up on this. We don't need the P dot. That's what all of this was for. And I'm slipped up on the algebra. R is on the inside and D is on the outside because everything's multiplied by D. So this expression right here. Oh, and we don't need the T's either because it's already being evaluated at the T. I messed up on how that operator works. All right. So R times this term. So, and you could actually factor out this instead, and it could be R plus 1 times all of this, but we just happen to do it like this. Okay, that should be good. And then for QB, so that would be an overall energy balance of the whole system. So really B and the enthalpy that our feed brings in are going to be the only enthalpy, or it's going to be the only energy going into the system. So QB plus ZF times we doing okay, yeah. So this is going to be moles. F times HL ZF. Z, yeah, okay. So that's everything going out. So QC plus, what do we have? So B times HL, and what is our mole fraction? XB plus D times HL. So it'd be this, but then if we want to get this by itself, I think that should be good. And then delta S is going to be, it should be right. Let's see what QC turns out to be. What's wrong? List is not a callable object. I don't know what that means. So it looks like we are going to have to hop off again.
All right.
Oh gosh.
Hang on.
Okay. So let's start. So we're going to have to graph out our punch on Savarot diagram. So let's start by making the outline for that. So we're gonna need fig2 equals make subplots. We're going to need that many rows and that many columns because we're gonna do two graphs. We're gonna make a punch on Savarot and then another McCabe-Thiele. Our x-axis, come on, x-axis is going to be our mole fraction. So we'll just call that z. So z equals np.ln space. We'll make that like we did the other one, 0 to 1 with 100 spaces. And now we can make our outline. So we'll do fig2.add scatter. So we're going to need, did auto-generate already find it? Yeah, so that's what we're going to, we're going to need a straight line for our vapor and liquid. So let's go ahead, color, we'll call that, this one will be black. Is the background white? Now the background's kind of a light blue, so we'll make this one white then. All right, and then we'll do the outline for our McCabe-Thiele, which is the same as just our XY diagram. So we'll steal this, throw this in here, fig2. All right, let's see how that looks. Okay. Oh, that's hard to see. Let's do, what do they call it? Powdered blue? Is that a name? No, that's not a name. Black and brown. Okay, that's actually kind of a cool shade of brown. So this is our HV, this is our HL, and then this is our 45-degree line and our XY equilibrium curve. All right. So let's to make these plots, we're going to need a equation for our operating line. That's going to be, so we'll do rectifying equation. It's going to be a function of x and y. We also have one for our stripping. Okay, so what we'll do is we will, running all of these under, or at least whenever we're trying to find a value of y, we already know what the x is in that stage. So what we can do is we can take the our equations that we have, and we can subtract both equations from each other, and that should, when they're at equilibrium, they should equal to 0. So we could just use a root scalar for whenever we need to solve for those. So we'll do, what do we call delta r? Delta r minus hv at y divided by hv at y minus hl at x minus xd minus y. We'll call it x and... No, we'll just leave it at x. Okay, we'll call this x y2 because it's y from stage n+1, which is the stage below, divided by y2 minus x. Now at equilibrium, these should equal 0. All right, same thing for this. So I'll copy and paste this. We'll have to tweak it though. So this is going to be delta S. This will be HL at just X divided by L X again, and then HV at Y2. This is going to be XB minus X over X minus Y2. And then for our very first Y, that should be equal to, or at least the first Y that we're going to look at, I guess we're going to work backwards on this. That'll be equal to XD. All right, so now we need our x's. That's going to be an array, xd. Same thing with y, xd. It's going to be an array starting at xd. All right, so now we need our tie lines and operating lines. So for I in range, we don't have to make it. It doesn't have to be that many times, but we'll go ahead and set it to 1,000. We'll start with tie lines. So fig dot add scatter to x equals y, and then y will equal, and these will be our tie lines. H L X HV Y equals 1 and column equals 1, go away. Mode equals lines. And then line, which one is it? Is it dots? Line. Come on, help me out, Python. Line. Is it dash? No. Line dash equals dash. Okay. Color will make this green. All right. So now we need our operating lines. So when we're above the feed stage, so when we're in the rectifying stage, so that's when x is going to be greater than CF if, oh, and this is fig too, I forgot. Something similar. But it won't be dashes and it won't be colors. And we'll make it red. No blue. But this is going to be x up to xd. This will be L, and then no, it'll be delta R, and then HL XD, rows, column equals 1. And then we need our Y values. So that's going to be, we're going to have a root scalar for that. So it's going to be it's going to be the root scalar of this rectifying stage equation. And our argument is going to be x. And of course, it's going to be the root of that equation whenever we apply x in there. But our bracket, so we're going to set up brackets. We're not going to do an initial value. We'll do brackets equal just a tiny bit above our bottoms feed, 1e to the negative 14th, and then a little bit below our final feed. Or no, it would be a little bit above whatever our x value is, and then a little bit below what our distillation composition is. All right. So then we're going to have the same thing for our stripping stage. So if x is greater than, x is less than zf, although it's going to be our stripping equation. And then we need this. It's going to be 2 delta s v of y. The x be 2x. Actually, no, the way that you want to do it is, if anything is, if x is below our xb, then no, we won't do that. We will break. But if it's anything else, we get this. Make these red. All right. Now, x's dot append x, and y's dot append y. All right, I'm going to come back and see if... Here, let's go ahead and run this and see what happens. Root scalar got an unexpected keyword. Brackets, is it just bracket? If insan, the function value at solver cannot continue. Okay, I definitely do not know what that means, so we'll be right back. Okay, found out what happened. I completely forgot to actually return anything out of here. So we defined our equations, but we did not return it, so no wonder the root scalar is not working. Also, there were a few mix-ups that I need to fix. So this should be HV, Y, L, X. And then should be X, and this should be XD, X. Oh, this should also be Y right here. I think that should fix it. F and B must have different signs. Oh, come on, buddy. All right. All right. Found out what was going on. So back here, we did it right on paper, but we just slipped up. This is supposed to be a minus. And then all the way back here, we messed up. These X and these Y's are supposed to be switched, which means that anytime that we use interpolated values, we've had our X's and our Y's switched up this entire time, which is not good. So we'll run all of these. All right. So there's our Pitt Ponchon Savarit diagram. Looking pretty cool. Let's do orange instead of red, because red is looking kind of harsh. All right, I think that looks pretty neat. And we will be right back to finish our McCabe-Thiele graph. All right, so to wrap this up, we need our staircase on our McCabe-Thiele. We'll go ahead and take this, although let's not. Let's do what pink. Auto generated comes in handy. It's going to be the same thing, but we'll need staircase. And we'll have that be black. Alrighty. Yeah, that's everything, and that wraps up homework. Homework 3 Part D.